Today we are going to learn about understanding neural network activation functions. In this video, you will explore how activation functions shape neural network outputs and their role in introducing nonlinearity. By the end, you'll understand various activation functions and their applications, equipping you with the skills to select the right function for your neural network models.
Welcome to our exploration of neural network activation functions. Activation functions are a critical component of neural networks, serving as the gatekeepers that decide whether a neuron should be activated or not. At their core, activation functions introduce nonlinearity into the network, a necessary feature for the network to model complex, real-world data. Without these functions, a neural network would simply be a linear classifier, severely limiting its capacity to solve intricate problems. Throughout this video, we will delve into various activation functions, understanding their unique roles and how they impact the performance of neural networks. Whether it's simple binary classification or sophisticated deep learning tasks, activation functions are at the heart of making it all possible.
Nonlinearity is a cornerstone of neural networks, enabling them to learn and model complex patterns. Imagine a world where neural networks could only perform linear operations. They would be unable to capture the intricate relationships in data necessary for tasks like image and speech recognition. Nonlinearity transforms a simple, linear model into a powerful tool capable of approximating virtually any function. This transformation occurs when activation functions introduce nonlinearities between layers, allowing the network to map inputs to outputs in a sophisticated manner. In multi-layer networks, each layer's nonlinearity compounds, enhancing the network's depth and learning capacity. This ability to model nonlinear relationships is what sets advanced neural networks apart, making them indispensable in a wide range of applications from autonomous vehicles to natural language processing.
The sigmoid activation function is one of the most well-known and historically significant functions used in neural networks. Characterized by its smooth, S-shaped curve, the sigmoid function takes real-valued inputs and maps them into a range between 0 and 1. This property makes it particularly suitable for binary classification tasks, where outputs need to be interpreted as probabilities. However, the sigmoid function does come with limitations. One of the most notable drawbacks is the saturation problem. When inputs are too high or too low, the function's output tends to saturate at 0 or 1, which leads to a vanishing gradient. This vanishing gradient problem can significantly hamper learning in deeper networks, as the gradients become too small for effective weight updates. Despite these limitations, the sigmoid function played a crucial role in the early development of neural networks and continues to be a valuable tool for specific applications.
While the sigmoid activation function has its merits, it is not without significant limitations that can impact the performance of deep networks. One major issue is the saturation of the output, which occurs when inputs are either very large or very small. In these cases, the derivative of the sigmoid function approaches 0, leading to a vanishing gradient. This vanishing gradient problem can impede the learning process in deep networks, as the weight updates become negligible. Additionally, the outputs of the sigmoid function are not zero-centered, which can lead to inefficient weight updates and slower convergence. These drawbacks have led researchers and practitioners to seek better alternatives, especially for deep learning tasks. Despite its historical significance, the sigmoid function's limitations underscore the need for more robust activation functions in modern neural network architectures. The rectified linear unit, or ReLU, has become one of the most popular activation functions in modern neural network architectures. Its appeal lies in its simplicity and efficiency. Unlike the sigmoid function, ReLU outputs range from 0 to infinity, effectively addressing the vanishing gradient problem that plagued its predecessors. This property allows ReLU to maintain strong and consistent gradients during training, facilitating faster convergence even in deep networks. The function itself is defined as fx equals max 0, x, meaning it outputs the input directly if it is positive, and 0 otherwise. This straightforward approach has made ReLU the foundation for many contemporary architectures, providing the nonlinearity necessary for complex pattern recognition without the drawbacks associated with older functions. Its efficiency and effectiveness have led to its widespread adoption in the field of deep learning. While ReLU has many advantages, it is not without its own set of challenges. One such challenge is the dying ReLU problem, where neurons can become inactive and stop learning if the input is always negative. To address this, several variants of ReLU have been developed. The Leaky ReLU introduces a small, non-zero slope for negative inputs, allowing for some gradient flow even when the neuron is inactive. Parametric ReLU takes this a step further by making the slope a learnable parameter, providing additional flexibility during training. Another variant, the exponential linear unit, ELU, offers smooth transitions for negative inputs, aiming to improve learning dynamics. These variants of ReLU enhance the function's robustness and adaptability, allowing practitioners to choose the most suitable version for their specific tasks. Each variant brings unique benefits to the table, making ReLU a versatile and enduring choice in neural network design. The tanh activation function is another widely used function in neural networks, known for its distinct characteristics. Unlike the sigmoid function, tanh outputs range from -1 to 1, providing zero-centered outputs that facilitate more effective weight updates. This property makes tanh particularly suitable for hidden layers in neural networks, where balanced outputs can lead to better training performance. However, like the sigmoid function, 10H also suffers from saturation issues. When inputs are too large or too small, the gradients can become very small, leading to slow learning. Despite this, 10H is often preferred over sigmoid in scenarios where zero-centered outputs are beneficial, and it remains a popular choice for many practitioners looking to balance simplicity with performance in their neural network designs.
Selecting the appropriate activation function for a neural network is a critical decision that can significantly impact performance. Several factors should be considered when making this choice. First, the specific task requirements and the nature of the data should guide the selection process. For instance, binary classification tasks may benefit from sigmoid functions, while deep networks might require the non-linearity and efficiency of ReLU. Additionally, the depth and complexity of the network should be taken into account, as some functions like ReLU are better suited for deeper architectures. It's also important to balance performance with computational cost, as more complex functions may require additional resources. Experimentation is key, as different functions can yield varying results depending on the network and data. Understanding the trade-offs and limitations of each function will enable more informed decisions, ultimately leading to more effective and efficient neural network designs.
Activation functions play a pivotal role in determining the performance of neural networks. They influence key aspects such as training speed and accuracy, making them essential for effective learning. The choice of activation function can also impact the network's ability to prevent overfitting by affecting how well the network generalizes to unseen data. Activation functions contribute to gradient flow, facilitating or hindering the learning dynamics depending on their properties. For example, ReLU's ability to maintain strong gradients aids in faster convergence, while Sigmoid's vanishing gradients can stall learning. Additionally, activation functions contribute to network stability, helping to prevent issues such as exploding gradients. Overall, the right activation function can enhance a network's generalization capabilities, making it a crucial component in the design and optimization of neural networks.
Activation functions are at the heart of many real-world applications, driving advancements in fields such as image recognition, natural language processing, and autonomous vehicles. In image recognition, activation functions enable neural networks to learn complex patterns and features, allowing them to classify and identify images with high accuracy. Similarly, in natural language processing, activation functions help networks understand and generate human language, powering applications like chatbots and language translation services. Autonomous vehicles rely on activation functions to process vast amounts of sensor data, enabling them to navigate safely and efficiently. In speech recognition systems, activation functions facilitate the conversion of audio signals into text, improving the accuracy and reliability of voice-activated technologies. These applications showcase the versatility and impact of activation functions, highlighting their critical role in shaping the future of AI and machine learning. In conclusion, activation functions are a fundamental component of neural networks, enabling them to model complex patterns and solve intricate problems. Throughout this video, we've explored various activation functions, such as Sigmoid, ReLU, and 10H, each with its unique characteristics and applications. Choosing the right activation function is crucial, as it significantly impacts the network's performance, influencing factors like training speed, accuracy, and generalization capabilities. As you continue your journey in neural networks, I encourage you to experiment with different activation functions and explore their impact on your models. Understanding these functions will empower you to design more effective and efficient neural networks, driving advancements in AI and machine learning. Thank you for joining us in this exploration of neural network activation functions.